Welcome to Sigest, your fortnightly serving of digestible science from plant and food research.
Kia ora and welcome to Sigest. My name is James Sainsbury and we're here today at Ruakura. The topic of AI, artificial intelligence, is inspiring and exciting, but it can also be daunting and concerning, and exactly where it's going to take us has still been figured out. In this Sigest episode, we're talking to Sam Birch, who's based at Ruakura as a data scientist in the data application science team. And today, Sam is going to help us think about what AI can do for us, not so much in the utopian or dystopian future, but in the here and now. Sam, welcome.
Thanks, James. Thanks for inviting me along.
So before we go full immersion on AI, could you tell us a bit about your work and training background and how you ended up working on AI at PFR?
So I probably took a slightly unusual path into data science at Plant and Food. I have been probably fanatically interested in software development and computer graphics for most of my life, but I actually ended up training as an electrician after leaving school. And so I worked as an industrial electrician in factories and dairy plants and meat processing sites and all of those wonderful places for probably about a decade, I think. And then eventually decided I wanted to actually finish my degree, go back to university. When I was studying, I didn't actually have a clear idea where I wanted to work. I went back and did a computer science degree initially, and then started doing a maths degree, realised that was quite interesting as well. And eventually someone suggested I could apply for an internship at one of the CRIs. I saw some quite cool ones at Plant and Food Research, and I did a studentship here over the summer, and that ended up turning into a job a few years later, which I've really enjoyed.
That's terrific. So real intelligence has led you here, and it also leads us very nicely into what we're here to talk about today, which is artificial intelligence. In preparation for today, I looked up a definition of AI using a search engine, which presumably in and of itself relies on AI, and it came back with the science of making machines that can think like humans. What's your definition of AI when you're thinking about your work?
Well, I do actually quite like that definition. I think it probably encapsulates it pretty well. One of the issues with the term, of course, is that it's not very well defined, and everyone has a different idea of what artificial intelligence actually entails. From a technical perspective, a lot of the methods that make up artificial intelligence are not really intelligence-based. They're just algorithms that happen to look quite intelligent. But probably the intent behind a lot of the work that's happening in artificial intelligence now, particularly with things like large language models, is to make machines that really are not very algorithmic. They actually exhibit something that appears to be truly intelligent, whether that's true or not.
Good answer. We'll come back to that idea of truly intelligence and humour at the end of the podcast. But for now, in the early 2020s, there were a couple of new open source AI machines were released, and that seemed to cause a huge increase in discussions around the potential and danger of AI in our way of life. But of course, we've been interacting with AI long before 2020. So Sam, can you tell us about some times that AI has impacted your life outside of work in this last week alone?
Or, to be honest, I'm probably not even aware of most of the times that AI has impacted my life over the last week. Certainly one last night, I was listening to my Spotify recommendations. That, of course, is AI-powered. They have clever machines that choose the type of music they think I'm going to enjoy listening to, and some of the time it does a really good job. Some of the time it does not. Some other examples probably include advertising. Every time I pick up my phone to browse the internet or go near any website, there are AI recommender engines trying to decide what I'd like to buy and how companies would like to sell me more products.
And how well do they decide what you want to buy?
I think I personally have quite a strong aversion to advertising. So if I was willing to let my guard down a little bit, they'd probably do a better job.
Yeah, good answer. I agree. So moving back into AI in the workspace, and you've got a couple of projects on the go at the moment where AI is a big focus of what you're working on. One of which has had a big impact on my team, which is the bee biology and productivity team. And I was wondering if you could tell us a little bit about that project and what was involved in getting it going.
Sure. So that project, I was approached by Michelle Taylor asking if we could help automate the counting of varroa mites for a trial that they're doing to try and improve varroa control in hives. This project involved having bees crawl over sticky boards where the varroa mites would get stuck and removed from the bees, and at some later date someone would have to count the hundreds or thousands of varroa mite that were stuck to these boards so that they could work out how effective the controls had been at preventing varroa mites in those hives. It's quite a simple project in a lot of ways. I mean, really, we just want to count varroa mites. That's basically all that there is to it. But if a human is doing it, it's extremely laborious. It involves sitting in front of a station looking at these boards for long periods of time. It involves a lot of eye strain, discomfort, and to be honest, probably inaccuracy. It's very hard to count so many mites without missing some in the hundreds. So the idea was that we could automate some of that using some relatively basic computer vision approaches. We can train some computer vision models to detect varroa mites in images of these sticky boards, and then we could just use those to count how many mites were present on each. That was basically the idea, and in practice that's largely what we ended up doing. Went through a process of capturing the images of these boards. We annotated some of them to train the computer how to recognise varroa mites in amongst all of the debris and other things present on the boards. And then we went through a process of training these computer vision models, extending the annotations where we found shortcomings or other issues, and just revising the models a couple of times. And at the end of it, we were able to run these vision models across hundreds of images of sticky boards collected over many months and give an automated estimate of how many mites were present on each, which I'm guessing saved somebody quite a lot of very laborious hands-on work.
Very much so. I guess on that note, we would have students over the summer, and when they'd finished up for the summer, there was always a bit of a tally of the hundreds of thousands of varroa that they'd laid eyes on. So that's a thing of the past. But going back to the process, how do you tell a computer what a varroa looks like?
I guess from a practical perspective, it's quite straightforward. We basically just want to take a set of images which show the varroa mites that we're interested in and all of the other stuff that we're not interested in. And initially we just ask a human to manually draw a box around the things that we're interested in finding, and we build a data set that we can use for training. And once that step has been done, we then have a software pipeline where we will take a computer vision model and we'll test it against some of these training images for which we have manually annotated data sets, and we look at how well the model performs, and then we iteratively just update the model and improve the performance slightly as we go, do that hundreds and hundreds of times automatically. And over time, these vision models become better at recognising the things we're interested in and ignoring the things that we're not.
Excellent. And paspalum seeds, which tend to flower at the same time as we're collecting varroa, look very, very similar to varroa to the human eye. And so I was super impressed at how well the model managed to distinguish between those two things. Back to one of the points that you raised there, and something that we talked about a lot when we were implementing the image recognition software for the sticky boards, was the error rate that comes with any computer model. And it wasn't so much that was problematic, but that it's important to understand how that relates to what the error rate would be in humans. Would that be a fair assessment of considering error in computer modelling?
Yeah, definitely. Yeah. So any software system is going to have some issues, as I'm sure we're all aware, having watched the recent software breakdowns around the world. But as long as we can identify how those errors tend to crop up and quantify them in a reasonably robust way, then we can still use those software systems to do that counting task or whatever it's been designed for. And as long as we have a good understanding of how we can account for the errors and how they're likely to show up, and in particular how that compares to the error that would be there if it was done, through a manual human counting approach. Once you're using it at scale, of course, it's hard to see those errors because the point is that you don't have oversight over the system as it's running all the time. So you do want to understand quite well where those errors are likely to crop up, what kind of form they take, where the models that are being used perform well and where they don't. Make sure that you're using them within the domain that they've actually been trained for. There are a variety of considerations like that. But I think in this case, we were able to compare how the model performed against the human counts, because we have that from the training data sets, and we can compare it against previous trials. And there isn't a 100% agreement between how a human will count varroa and how a computer vision model will count varroa, but we're able to characterise how they interact and how those two approaches compare, and so we can still interpret the results in a meaningful way.
Yeah. Does the error rate go down the more these models are trained?
Yeah, to an extent. You definitely reach some diminishing returns eventually. So some tasks are quite hard. It depends on why the error is being introduced. When you start training a computer vision model, typically you will make a first stab at it and then evaluate it a little bit more. And in that initial evaluation, usually there's going to be numerous problems that crop up. But the reason that you do that is to quickly identify the types of images or the types of input data that is problematic and which the model struggles on, and you can use that to then select a whole lot more training data with those problems in mind and add that to the training data sets for these models as well. And after you've been through that process a couple of times or 3 or 4 times, usually the robustness of the model will go up significantly. At some point, you are just asking too much of either a computer or a human. Sometimes I think people would like to be able to just throw a computer at a problem and get perfect results, even when humans are simply not able to do it either. What's being asked of them is too challenging, too vague. Yeah. There's a lot of subjectivity, even with counting, there's a lot of subjectivity around what the results should actually be. You look at a sticky board, it's not always clear whether what you're seeing in front of you is actually a varroa. So should that particular one be counted or not? There's definitely some subjectivity there, and unfortunately that's true for computer models as well.
Yeah, hugely impactful project. Saved a lot of time for a lot of people. So the other project, which I thought it would be great to get some of your insights on, is the one looking at standardising the way kiwi fruit are evaluated. My understanding is that at the moment there's quite a few subjective measurements around traits such as colour, shape and size, and I guess that also takes time, but I'm also wondering, what's a beautiful golden colour to me might be a slightly different colour to somebody else. So you've thrown AI at this challenge and taken a look at changing the way that's done a little bit. Could you tell us about that?
Yeah, definitely. That's actually quite a large group of projects really, and to the extent that AI plays a part, it's only a part of the solution. The focus there is really to improve the quality and objectivity of these measurements that we take for fruit. It can be kiwi fruit or pears or apples or kiwi berries, all sorts of different things. But there's a lot of interest from a breeding perspective in being able to measure things like the size of internal regions of cut fruit or the colour intensity of different regions of the fruit when you're eating it, things like that. Now, some of those measures are inherently quite objective, things like the area of the core of a fruit. That's intrinsically continuous, precise measure that we should be able to take. But it's actually quite difficult, even with something like that, for a human to pick up a piece of fruit and say precisely what the area of this region is in square millimetres or as a proportion of the overall fruit. So even for these quite objective traits, it's quite hard to get precise, objective measurements for each of them. And then there's a whole range of things that are much less objective. As soon as you start talking about colour of fruit, you get into this incredibly subjective and complex area. It's very challenging to quantify the intensity of the red coloration of a piece of fruit in a consistent way between different people, different sites, different years, things like that. And so there's definitely been a push within PFR to improve the way that we approach these problems. And computer vision does help a lot to improve the quality of these measurements. A common approach at the moment is for technicians, for example, to pick up and visually look at a piece of fruit, and then they'll use a subjective ordinal scale to estimate traits, things like the core size or the colour intensity. But if we instead use computer vision and image capture, it makes it a lot easier to move away from those subjective scales to continuous objective ones. there's still inherently some subjectivity in the decisions that we make while writing the software, for example. We have to choose what colours we're looking for in a piece of fruit. We have to choose what traits we're looking for. There's a subjective component even with computer vision. But once you've made those decisions, the methods or the results that you get then become a lot more consistent and repeatable. And you can typically explain how they were reached, unlike asking a human why they chose a particular value on a scale.
Which is always helpful when you want reproducible data.
Yeah. And there's a bunch of other nice advantages as well. Things like, at the moment, when you look at a piece of fruit, typically only one or a subset of the possible measurements that are made are actually recorded at that time, because every additional measurement takes additional time, it's additional labour. If you are using computer vision, of course, that's not a problem. Once you've gone to the effort of capturing the image, all of the possible measurements that could be made can be made effectively for free. So the size or the coverage of your data sets goes up significantly, and the data sets that you build about your populations or your trials over time is much higher. Another advantage to using computer vision is that once you've collected these images, you can go back and retroactively measure new traits in old data, for example. If you come up with a new measurement that you want to make in 2 or 3 years' time, you don't have to wait for a new year or a new harvest before you can start to measure that. You can go back and measure it on all of your existing data, which also makes it a lot easier to share your data between teams or across different trials and things like that, because you don't need to know ahead of time which particular measurements need to be made to deliver value to your trial today and any others people come up with in the future. Once you have the images, you can effectively choose what measurements you want to make, and it doesn't require a high level of coordination between teams to achieve that.
Yeah, so huge wins and increases in efficiency and shifting things from being somewhat subjective or difficult to measure in an objective way to quite an objective space. And then there's also all of those wins about increasing capacity and ability to share data and move things forward and revisit data sets. So huge potential. So that's given us oversight of 2 really, really incredible areas of focus of AI right here and right now that have had a huge impact on what research is delivered and how it's delivered. Reaching forward 10 years, where do you think we could be with the use of AI in our science?
Well, that's a good question. I think it would be very, very challenging to speculate on where we will be in 10 years, given how much things have changed over the last 2 or 3. But even ignoring where we could go in the next 10 years, I think the tools that we have today have a huge amount of unrealised potential. And I would love to see better access to those tools at PFR, better understanding of what's available, how you can use software development and computer vision and artificial intelligence and all of those sorts of tools in your work to get better results, to make things more efficient or more objective or more repeatable or save people large amounts of work. And yeah, I'd love to keep working on that.
So we're almost out of time today, but I did want to ask you about large language models, which I understand is the type of AI that underpins things like ChatGPT and Bard. Is this a type of AI that you've played around with, either at work or otherwise, and what are your thoughts on it?
Yeah, interesting question. So I'm not developing software systems that use large language models in my work here, although there are other people at Plant and Food Research who are actively looking at that. But I definitely use ChatGPT and similar tools in my work. And to be honest, I'm quite astounded by how well they work. I don't think we've achieved true general intelligence here, but despite that, they still work shockingly well. I use them for a mixture of professional work and as a software engineer, and also just for general queries about day-to-day life. Sometimes I'll think up curveball questions that I feel like the AI surely can't get right, but it continues to astound me. I think it's a really interesting area actually, and I'd like to see large language models used at places like PFR more to support our professional research and the work that we're doing. I know there's probably a little bit of pushback against having them in things like your television and your cell phone. Sometimes it's nice to not have AI pushing its way into every aspect of your life. but as a tool for professional work and for understanding research and for understanding operations at a company and just being more efficient in those areas, I actually think they're really fantastic.
So that observation about true general intelligence is an interesting one. And I read an article about a year ago that was asking whether AI can make a joke. Does it have a sense of humour? And the conclusion at that stage was not really, because, jokes often rely on unpredictability, whereas AI is like nothing but prediction. But that was a year ago. So to wrap up today, I thought I would take a look and see if one of these large language models could tell me a joke about data scientists. Are you ready for it?
I'd love to hear it.
How do data scientists stay cool during the summer? They have plenty of fans and they know how to minimise their temperatures with optimal algorithms.
Well, I like the comment about us having lots of fans.
So while I can't quite imagine a human saying anything like that, there definitely appears to be some humour there, all of which is to say AI appears to be making progress in the joke department. And I guess thinking back on some of your observations, AI does have an error rate. Sometimes there are misses, just like humans. And to be fair, human humour can also miss sometimes. So perhaps it's on the right track. We're at the end of our time here today, Sam, but really just at the beginning of a discussion about the potential of AI in the here and now. Huge thank you for coming in today and sharing your thoughts and perspectives, and being from a team of former Varroa counters myself. We are very much a testimonial to the power of AI to bring change to some of our work. Thank you.
Thanks a lot for inviting me along, James.
And thank you out there for listening. Please check out the Sigest pages on our Plant and Food website for extra links and to see our full catalogue of podcasts. Please follow or subscribe to our channel on iTunes or your favourite podcast provider. And to help this channel grow, please post a review and rate this podcast. Mā te wā, until next time.